once again in the unenviable position of following Thomas. Anyway, I'm Martin Swany. I'd like to talk a bit about network systems engineering. I've been remiss in listing my collaborators here. In fact, my chief collaborator, Ezra Kissel, is running a program project meeting here, which we just were lucky enough to schedule during the middle of this exciting and busy week. So he's not here, but he and a host of students have been involved in these various projects. So I say basically this is the first bullet of every talk I've ever given ever, I think, which is that computing environments depend on networks and that the performance of networks really drives their efficacy. I think it's fair to say that most interesting applications depend on communication, depend on networks in some way. Bandwidth is easy. You can just you can lay more wires. You can pay money to get more to get increased bandwidth. But latency is more difficult. There are no you can't really play games with the speed of light, and so basically we have to think about ways to shave off latency for when there's a control loop involved. When there's something that latency is that is sensitive to latency, then that is a significant problem. And then unless power is a concern, we've been moving into smaller and smaller devices, and then bandwidth's difficult too. So teasing the performance and out of network systems involves techniques that span all sorts of architectural layers, software, hardware, protocols, and approaches. So my group and I work on various aspects of networks, from data centers to lightweight environments and edge computing. So when I say that latency is critical, essentially the way to address that is to make the network smarter. Networks were traditionally designed just to move bits. In fact, for a time, it was anathema to talk about the network being anything other than a passive mover of bits. And I mean, in the Internet Engineering Task Force that guided the formation of the internet, which we all depend on, literally it was, considered, there was a significant war over basically any intelligence in the network. The guiding principle of the internet, coming from the end-to-end arguments in system design, says it's a bad idea to put smarts in the network. And so I like, annoying those folks, and our whole work is about shaving off latency by putting smarts in the network. So with software-defined networks that allow you to control routing on a fine-grained level, smarter network interfaces, and network processing elements that we place in the network fabric. The key network processing element that we are working on these days are field programmable gate arrays, or FPGAs. These have moved from sort of a specialized device that you might use for data acquisition, or which you might prototype a processor or a device on, to something that people are recognizing has utility from the data center to edge computing. Intel, maker of the general purpose CPU that you've heard of, invested in Altera, maker of FPGAs, and spent $14 billion sort of hedging their bets that maybe these specialized devices are here to stay. Good deal. So we're investing a lot in them. And I'll also say that, that whereas FPGA programming was taught in various sort of curricula, it's a way you might learn how a processor works, programming in Verilog, people don't think of them as being something that you build a system around until today, I think. And so in intelligent systems engineering, we are probably one of the few places that's training students to actually consider these as a part of as a first-class entity in system development. So we put them in the data center network. That looks interestingly terrible, but you can see that the curves go up and to the right as they're supposed to. Although actually, our line is the lower purple line and the green line, which you can't really see because it has very high performance, very little variance, even as we move to larger and larger communication sizes. This is for collective communication, which is a significant problem in high performance computing. We're also putting them at the edge. We have a model that is that basically says for edge computing, if we have a simple stream processing sort of element, we can improve performance as long as we have an execution model that is limited enough for us to be able to process a packet at a time. And our initial results in a recently submitted paper show, when I say over 1,000 times, I mean actually 23,000 times speed up over traditional sort of software and stream processing elements. So that is my story. Thank you.